করছিলাম। Previous week we have seen about the technology for preparing the nanomaterials. The technology we have seen is sol gel process, by which we can prepare bulk nanomaterial, we can prepare thin films, or we can prepare aerogel or aerogels by sol gel technique. Actually, this technique is very much popular to the chemists because it is a chemical technique. So it is very popular to the chemists. So we have studied it in details. Now we will go to study the deposition technique. That means preparing a nano film or preparing a thin film by the deposition of bulk material or from the deposition of bulk material. So there are a lot of methods to prepare the thin films. There are hundreds of methods, I think, to prepare the thin film of nano width. Thin film of nano width. We'll see a few, 4 or 5 of them, but the most popular one we'll see. But there are many other ways to prepare thin film of nanomaterial. So let's start about this. Vapour deposition technique. Vapour deposition technique means we will prepare a vapor of a material. Say, for example, we shall prepare a vapor of a metal, and then we shall deposit it on a substrate. We shall deposit it on a substrate. That is known as Vapour deposition technique. This is of 2 types. These are of 2 types. One is physical Vapour deposition, and another one is chemical Vapour deposition. So what is a Vapour deposition? Vapour deposition is the deposition from vapor phase of a material. That means you have to make a vapor of a substance, of a material to whom you want to deposit, to that material you want to deposit, and then condense it in a substrate to prepare a thin film. So again, we'll see it again. Now, first we see what is a thin film. What is a thin film? You'll see here this picture. You'll see that silver colored material or above above the your material there is a film. It is very thin, so it is called thin film. Thin films are thin material layers ranging from fraction of a nanometer to several micrometer in thickness. The, the thickness of this material, of this film, the thickness not of this material, of this film is from the nanometer to several micrometer. As because it is very thin, so it is known as thin film. So what is a thin film? A thin film is a layer of material ranging from fractions of nanometer or several micrometer in thickness. Second is how a thin film can be made. A thin film technology is a self-organizing structural evolution. That means this film is made by the self-organization of the elements, by the self-organization of the elements. From ancient times, people already knew how to make the thin film. They made gold thin film to see, to show any material golden. They make a thin film of gold on a substrate, on a substance. So this preparation of thin film is known from the ancient times. Now, why thin film? Why thin film is prepared? It is prepared to maintain surface uniformity, to make the surface uniform, to reduce the amount of light absorbing material. That means to reduce the amount of material. Say, for example, you have a watch of a stainless steel. Now, if you coat this watch with a thin film of gold, then your watch will be made of gold. It will show golden luster on it. So the amount of or the mass of light or the mass of substance will be reduced in the thin film. This can be done by spray coating. This you can say, for example, we can spray paints in our say, for example, car. You have seen the cars are sprayed, paints are sprayed on the car. It is a thin film of paint on the car. Why? To see the if you spray paint, you will get the surface uniformity. You will get the luster of color. Huh? So thin film is required to make the surface uniformity and the what it is said to reduce the amount of light absorbing material. Sometimes some substances present in a material which absorbs the light. If you apply a thin film coating on it, then it cannot absorb the light. It will show the luster of color. So to reduce the light absorbing substance, you can also use the thin film. To decrease the weight and bulkiness of the material, if you use the thin film, then your weight is decreased of the material. Now, there are some applications of the thin film. It is now applied in microelectronics, just such as CPU processors, in your cell phones, in your iPads, in your solar panels. Uh, in the solar panel, you use the thin film. You see, this watch is the golden watch. Is the golden watch. Actually, in that watch, a thin film of gold is coated. So we call it a gold watch, but it is actually a stainless steel watch. A thin film of gold is coated here. So in different places, you see here a thin film of paint is sprayed here to give you bright color of the scarf. And you see here a thin film of metal is given here. It is a strip of medicine what you use. This is a strip of medicine. Here thin film of say for example aluminum is given here. So there are many uses of thin film. Now our intention our intention is to make thin film of nano range, say for example 10 nanometer or 50 nanometer or 100 nanometer of wood. That means we want to make thin film, that means a two-dimensional nanoparticle, which we call quantum well. Our aim is to prepare a thin film of nano range. Now, for that, we will deposit atoms on a substrate. We'll deposit atoms on a substrate such that the width of that film is in nano range. For example, you see, let us suppose this is a substrate. The green one is the substrate. On that green substrate, you have prepared a thin film of silicon dioxide. You have prepared a thin film of silicon dioxide. Why it is thin film? Because you see this width is in nanoscale, say for example 10 nanometer or 20 nanometer. The width of this film here, I think it should be called breadth of this. It is in nanoscale, so it is called thin film. So on that thin film, you can again deposit nickel, another thin film, or you can deposit carbon on that again. So you can have a multi-layer of thin film on a substrate by deposition. That means what do you mean by deposition? Say for example, these nickel atoms are deposited on that film. The carbon atom is deposited on that film. So this is known as deposition. What is deposition? Deposition is applying a thin film on a surface, ranges from nanometers to micrometers. Applying a thin film on a surface ranges from nanometer to micrometer. Now, this thin film application, we cannot apply this thin film by our hand. Say, for example, we can paint our wall. What is the painting on a wall? That means applying or making a thin film of paint on the cement of the wall. We can do it by our, say, for example, a brush or something like that. We can do it by ourselves. But if it is a nanoscale, if it is a nanoscale thin film, say, for example, what do you mean by nanoscale? Nanoscale, say, for example, its height, the height of the thin film, say, the height of the thin film is of two atoms, one atom and another, the layer of one atom and layer of another atom. So if the height of the two atom, if the film of the height of the two atom, we cannot prepare it by our hand, or we cannot apply it by our hand. It will be more thick. You see, your paint on the wall or paint of the car, it is thick. It is, say, for example, 1 millimeter thick. But we have to prepare the thin film of around 10 nanometers. So you cannot do it by your hand. So how can you do it? How can you apply? How can you prepare a thin film? By the self-assembly of the atoms. What do you mean by self-assembly of the atoms? Say one layer of your atoms deposited here, and another layer of atom will be deposited here by their self. They will deposit by their self. That is called self-assembly. They will deposit by their self. So this is one layer of atom and this is another layer of atom. It will be deposited by their self. We cannot do it. We cannot handle so tiny atoms. So tiny, we cannot handle so tiny atoms. So it is self-assembly. And we will see how that atoms will be assembled in future slides. But to prepare a thin film, the most important thing, we want a substrate. What is a substrate? On which that thin film will be grown or prepared. That is called substrate. Here you see the green thing is known as substrate, and upon this green substance, the thin film has grown. This thin film has grown. This is this is a multi-layer thin film. First layer of silicon dioxide, say, for example, second layer is of nickel. It is a multi-layer thin film as your requirement. There are different techniques for the deposition, like PVD, physical vapor deposition, chemical vapor deposition, sputtering, electroplating, and coating, etc. There are different techniques of this deposition. We'll see some of these techniques. Now, synthesis of thin film, that means how can you prepare the thin film, or how can you deposit the thin film actually. This thin film deposition is of two types. One is physical deposition and one is chemical deposition. One is physical deposition, that means by physical way, and another one is chemical deposition, that means in chemical way. This physical deposition again is of two types. One is evaporation and another one is sputtering. The chemical deposition is chemical vapor deposition and atomic layer deposition. We will see all of them one by one. Now, first we see that physical deposition. What is that physical deposition? It also called physical vapor deposition. So what we have to do? What we have to do? We have to vaporize first. If you see this slide, say for example, this is a source of material. Say for example, you want to make a thin film of aluminum. For example, you want to make a thin film of aluminum. So this is the source or the target, we whatever we can call. This is the source or target. What is the source or target? The source or target is aluminum. Now, we have to first vaporize the aluminum. That means aluminum solid. We have to bring them in the gaseous phase. So we have to vaporize the aluminum. That means the aluminum atoms are now free. The one aluminum atom, two aluminum atom in the vapor, the aluminum atoms are free to move. So we make the aluminum atom in the gas phase so that it becomes free. And this vapor, aluminum vapor, we want to condense upon a substrate. So we have kept a substrate here. Say, for example, from here, we are vaporizing aluminum and we have kept a substrate here. So aluminum vapor is going to the substrate and condensing on that substrate. That means from vapor phase, the aluminum is again in the going to the solid phase. So vapor, say for example, there are 100 aluminum atoms here. So one by one, they are attaching with the substrate, that make one layer. And after making one layer, they will make the second layer of aluminum. And if our desire to make a thin film of 2-layer width, then we will stop the vaporization now and we will get a thin film of 2-layer width. So first you have to vaporize the aluminum. Then the free aluminum will condense here. Here, one by one, it will condense here. And it will make one layer first, monolayer. And if we are satisfied with that monolayer, then we'll stop the vaporization and we'll get a thin film of monolayer. If we want a double layer, then we'll stop the vaporization after 2 layers is made. Then we'll get 2-layer your thin film. So how can you understand, or how can you see that there are a monolayer of aluminum or bilayer of aluminum is produced? You have to characterize the thin film. You have to characterize the thin film, whether a monolayer of aluminum or bilayer of aluminum is condensed. So how can you characterize? There are some instruments by which you can characterize. Sometimes these instruments are attached with the machine you are doing that experiment. Sometimes you have to take the thin film and you have to place that thin film to another machine. So in the physical vapor deposition, first you have to vaporize a solid substance, then you have to condense that vapor on a substrate. That is the physical vapor deposition. That is the physical. That is the main thing of physical vapor deposition. To vaporize a solid substance, to vaporize a solid material, and then condense the vapor on a substrate. That is the main thing of physical vapor deposition. Physical coating process involves condensation and evaporation of material. PVD is used for high melting point and low vapor pressure material. Generally, it is used of high melting point material and low vapor pressure material. PVD is carried out at high temperature and vacuum. Physical vapor deposition is carried out at a high temperature. Why high temperature? Because high temperature is required to vaporize a solid substance. And in vacuum, why vacuum is required? I will tell it later. On the contrary, to PVD, CVD means chemical vapor deposition, is a method in which chemical addition or chemical deposition occurs. What is that chemical addition or chemical deposition? We'll tell it later when we study the CVD. Now, the main slide is again, high temperature is required to vaporize the material, and vacuum of different ranges is used to depends on the mean free path used, which depends on mean free path requires the system. Now we'll tell about this, why vacuum is required. First we see first we see the application of PVD. PVD methods are commonly used in following: circuit and IC fabrications. For the circuit fabrications, generally PVD method is used. Aerospace in TBC and transparent coating, reflectors and optics. TBC means thermal barrier coating. In aerospace, there are some coatings called thermal barrier coating in aeroplanes or rockets. In that case, PVD method is used, or transparent coatings, and reflectors and optics. Now we'll see the main thing, how we can make a thin film by physical vapor deposition. Now, one of the process is evaporative deposition or deposition by evaporation. What is that method? You see here, this is the instrumentation, a very simple instrumentation. Here you see, here you will place the target material or object. That means, say for example, aluminum. You want to make a thin film of aluminum. So you will place bulk amount of aluminum here. Say for example, a aluminum rod or some aluminum powder or some aluminum chips here. And you heat the aluminum, this aluminum powder or rod, whatever you have kept here, you will heat that by means of this heating coil. Generally, this heating coil made of a high temperature coil, say for example titanium, rhodium, that type of coil. Uh, mm, you will heat this aluminum with that coil. Now, when you heat this aluminum, the aluminum will vaporize, and it will go through this way, and here you kept the substrate on which you want to deposit the thin film. So this aluminum atoms now, when aluminum is vaporized, it becomes aluminum atoms. Aluminum atoms will go here, and it will be condensed on that substrate. This is the simple process of evaporative deposition. Now, first thing, you require a vacuum here. What is vacuum? Vacuum means you have to make out all the air from this instrument. So you require vacuum here. Why vacuum? Because of two things. First, say for example, air is here. Air means what? Air means nitrogen. Air means oxygen. Air means water vapor, and all these things. So when aluminum starts to go through this substrate, it will collide with the nitrogen atom, or say oxygen atom, and it will deviate from its path to this way, through this way, or to this way. So aluminum atom cannot go to the substrate, or a large fraction of aluminum will collide with the air molecules, and they will not go to the substrate. Now, if the aluminum atom will not go to the substrate, then we will not get desired amount of product. Now, for that vacuum is necessary. And second thing, air contains many molecules, and these molecules will also be deposited here. Say for example, aluminum is going to this way, and in the path of aluminum, some oxygen atom comes here, and it makes aluminum oxide, and aluminum oxide will be deposited here. But we want a aluminum thin film here, and we will get aluminum oxide contaminated or aluminum nitride contaminated thin film here. So this thin film will be contaminated. So you require the vacuum here. You require the vacuum here. Now, how to make the vacuum? We have machines. We have machines to make this vacuum, to make air out from this chamber, and the scale of vacuum is known as torr. Torr, we will 10 to the power minus 2 torr, 10 to the power minus 3 torr, 10 to the power minus 5 torr, 10 to the power minus 15 torr. That means that much torr means 10 to the power minus 15 torr means almost nothing is there. No, no vapor, nothing is there. No air, no vapor, nothing is there. So it is very hard to achieve actually. It is very hard to achieve 10 to the power minus 13, 10 to the power minus 14 torr. It is very hard to achieve. Generally, vacuum about 10 to the power minus 2, 10 to the power minus 3 vacuum is done. But above this, 10 to the power minus 5, 10 to the power minus 6 also can be done. But above it, it is very hard to achieve. It is hard to achieve. Now, if we see second slide of this, if we see the second slide of this, here you see the material is kept on a board. You see this is a crucible, and the material is kept on it, and heating is done under or heating is done by this way. Then vapor is coming, aluminum or something, whatever it may be, vapor is coming to the substrate, and this is the substrate holder, and it should be a vacuum here. There should be a vacuum here. There should be a vacuum here. Otherwise, you will not get the thin film of desired substance, or you will get it too much of time. It will kill too much time. It will require to get this thin film. This is another simple simple schematic figure of the thin film. Now, do you? Ooh. Now, do you have any question on that? This is the fundamental thing of physical vapor deposition. This is the fundamental thing of physical vapor deposition. Do you have any question on that? Then we'll go to the next phase. Have you understood? All of you understood? What is physical vapor deposition? What is thin film? And what is the primary requirement? The primary requirement, actually, you have to, the vacuum, the substrate, the material, and heating element, and the vacuum. This four is the primary requirement. Without vacuum, you cannot make a thin film. So you have to have a vacuum system attached to it, and the higher is the vacuum, your thin film is then pure to pure and pure. The higher is the vacuum, and the purity of your thin film will be higher. Will be higher. So আমি তো অনেককেই দেখতে পাচ্ছি না। হাফসা আছো তুমি?
জি স্যার, আমি আছি।
হ্যাঁ, রাশেদ খান আছো?
জি স্যার।
কি ব্যাপার, তোমাদের এগুলো দেখা যাচ্ছে না কেন? ঘটনা কি? আমি ওখানে চলে গেলেই তোমরা বন্ধ করে দাও কেন? সমস্যাটা কি? মঞ্জুর এলাহি তো নাই মনে হচ্ছে। So যেটা বলছিলাম, this is the main requirement of physical vapor deposition. Main requirement of physical deposition. Do you have any question? তোমাদের কোনো question আছে তো বলো এখানে। আমরা এটা হচ্ছে very primary thing. Now the next one, is the electron beam vaporization system. Now, these are the process of vaporization. The main theory of making thin film is same, but these are the process of vaporization. So in the evaporative deposition, what we have seen, we have heated the target material. We have heated the target material, and then the target material became vaporized, and the vapor is condensed on a substrate. Now, by not giving heat, how can we vaporize? How can I vaporize a material? By not giving heat. So this is one process, what is called electron beam vaporization technique. What is that? A beam of electron is bombarded with that target. That means a beam of electron which is produced from an electron gun. From an electron gun, we'll see it later what is an electron gun on when we'll study the STM or SCM or TM. The electron gun means which produces electron, and it makes electron out just like a bullet. That is called electron gun. Now, from electron gun, we will produce some electron and hit that electron on the target material. The target material, I told you, say for example, it is aluminum. Now, when this electron will hit the target material, some heat is produced there due to heating. If you rub this thing, some heat is produced here. So when electron will hit to a material, some amount of heat is produced here, will be produced here. This heat will vaporize the metal or the target material. So this is a vaporization technique. The main technique is like evaporative technique. It is a vaporization technique by the electron gun. So electron beam is generated by tungsten filament in the electron gun, and the material is placed here in a graphite or tungsten crucible. Deposition mechanism is same, and deposition is carried out under high vacuum. Why high vacuum? Because without high vacuum, electron beam will collide with the air molecule or other molecules present in the chamber. So it will not be bombarded here. So your it requires a high vacuum here, and then from the electron gun, electron beam is allowed to bombard on the target material. And when it bombards the target material, some heat is produced, an amount of heat is produced there, which evaporates the target material, which will go to the substrate and makes the thin film. This is the electron beam vaporization technique. This is the electron beam vaporization technique. We'll see the figure here. Same thing. It is a high vacuum. It is in high vacuum. Now, from this electron gun, electron beam is allowed to bombard on the substance. Now, why it is bent? It is bent because if you allow it direct hit, then it will hit to a small portion of the of your target material. But if you bend it, it will hit whole crucible, whole the material of the crucible. Then heat will be produced in the whole of the material of the crucible, and large amount of your target material will be evaporated to go through to the substrate. This substrate is also heated. This substrate is also heated here. And this is the crystal thickness monitor. That means how much thickness, the thickness of the thin film monitor. How much thick is the thin film? You can monitor by this way. So it is a electron beam evaporation system. There are other methods also, which is known as pulse laser deposition technique. What is pulse laser deposition technique? You know what is a laser. I have explained to you what is a laser. Now, if you allow a laser of high energy to hit the target material, then it will produce heat there on the target material, and the target material will make a plasma. What do you mean by plasma? Plasma means it is a condensation, or it is a combination of ions. Say for example, in a chamber, in this chamber, there are argon gas. If you ionize all the argon atom in this chamber, or most of the argon atom of this chamber, then this chamber is known as with argon plasma. So what do you mean by plasma? Plasma is a state of ions. Plasma is another state. We have solid state, we have liquid state, we have gaseous state, and we have a state of plasma also. Now, where the most of the substance are in ion or in ionized state, then we call them in plasma state, or we call them in plasma. So in plasma, what are the substances in plasma? The substances in plasma is mostly the positive ions, some electrons, and some unionized atoms. It is a mixture of positive ion, electrons, and unionized atom. Say for example, here in this chamber, there are 100 argon atoms. So in plasma, say 90 of that 100 argon atom is ionized. So you will find what? Some 90 argon ions, 90 electrons, and 10 neutral argon atom, that means 10 unionized argon atom. So in this argon plasma, here you will it is a mixture of argon ion, electron, and undissociated argon atom. So what will happen if you hit the target with a laser, with a high intensity, high powered laser? Then heat is large amount of heat is produced here. Large amount of heat will be produced here. So this heat, what will this heat do? It will vaporize the target material. Say for example, if it is aluminum, then it will vaporize the aluminum material, and from aluminum, it will ionize the aluminum also. It will vaporize the aluminum and it will ionize the aluminum also, because the strength of this laser is very high. High powered laser. The strength of this laser is very high. So this high strength laser will ionize the vaporized aluminum atom to form a plasma. This plasma will go to the substrate, and it will form a thin film here. So you see, this is the this is more clear picture. It will be a high vacuum system, and there high in here some argon or something will be present here, can be present here. But what is the main thing? This is the laser beam. It attracts the it is the target material. Say for example, it is gallium arsenide or something, and it will attack this target material. This target material is vaporized and ionized to form a plasma. It is also called plum, P-L-U-M-E, plum. It is also called plum. This plasma will go to the substrate. Why it will go to the substrate? Say for example, all plasmas are positively charged. Then if you make this substrate holder negatively charged, or if you make this substrate negatively charged, then it will attract the plasma towards itself, and this type of thin film will be produced. This is your plasma laser deposition. Pulsed laser deposition. Now, high vacuum is required for why? Because if there are other molecules are there, say for example, nitrogen molecules or oxygen molecules are there, then they will ionize also, because very high amount of heat will be generated here because of the laser beam, high energy laser beam, and they will produce your plasma also, which will say for example, oxygen ion will also deposited here, which will contaminate your thin film. So high vacuum is required. High vacuum is required here, and you will get a very good quality of thin film. Actually, the quality of the thin film depends on the purity of the target material. Say this is aluminum, and on the purity of that aluminum, you will find the pure aluminum, pure aluminum thin film. কার মাইক্রোফোনটা অফ, এটা অফ করো তো, আমার মনে হয় এর মাইক্রোফোন, নাফিসার মাইক্রোফোন নাকি?
স্যার আমারটা তো
তাহলে কারটা অন আছে?
রাশাদ খানের টপ
একটু অফ করো। অফ হচ্ছে? Okay, so the vacuum is required, high vacuum is required for two things. One is I told you, one is about the mean free path. Can you remember the mean free path of first year kinetic theory of gases? What is the mean free path? When gases are allowed to move, then what is the kinetic theory? They move here and there and they collide with each other. This is the kinetic theory. And what is the mean free path? Mean free path means a gaseous molecule before collision, the path it is traveled before collision is known as mean free path. A gaseous molecule travels from here to here before collision. Then the mean free path is from here to here. Now, if vacuum is there, then this gaseous molecule, the gaseous, say for example, the gaseous aluminum molecule will travel from here to here. If it is high vacuum, then the mean free path will also become higher or larger. Now, if there are some molecules here, it is not highly vacuumed, some molecules are here, then the gaseous molecule cannot go here because its mean free path becomes less. Why less? It will collide with the molecules of air on his path of going to the substrate. So we have to increase the mean free path of the vapor molecule. To increase the mean free path of the vapor molecule, we have to make the whole chamber highly vacuum. The whole chamber must be highly vacuumed. Why? To increase the mean free path of the vapor molecule, so that it can travel all the way to the substrate. Otherwise, you will not get if the gaseous molecule cannot travel to the substrate, and in its path it will collide with somebody, you will not get the proper your thin film. So high vacuum is very much required to make the thin film. So this is the pulse laser deposition. This is the pulse laser deposition. Now, the advantages and disadvantages of this vapor deposition. Line of sight deposition allows the use of mask to define areas of deposition. What is the line of sight deposition? Line of sight deposition means, you see, here is the target material and here is the substrate. It is directly in the path of the substrate. Say, for example, if the substrate is here, then it is not line of sight, your line of sight deposition. The line of sight deposition means the gaseous molecule will go directly to the substrate. Now, what they call the line of sight deposition allows the use of mask to define the areas of deposition. Say, for example, you want to deposit thin film here and you want to deposit thin film here. You don't want to deposit thin film in between it. Then what will you do? You will keep some substance here that is called mask. You keep some substance here so that the gaseous molecule cannot condense here. So that the gaseous molecule cannot condense in this region, you will keep some substance here that is called mask. It can condense here, it can condense here, but it cannot condense in between here because you have kept some substance there. You have kept some substance there, and after this thin film is produced, you will make that substance, that mask, out from the film, and you will get this type of thin film. So this is the first advantage. Second advantage, high deposition rates can be obtained. You can get a thin film, say for example, in pulsed laser deposition. In pulsed laser deposition, you can get a thin film of about 15 minutes, within 15 minutes. High deposition rate is obtained, can be obtained. And the deposition rate can be easily monitored. It is easily monitored. I have shown you that this is the crystal thickness monitor. It can be easily monitored here. And the other most important thing is the vaporization source material can be in many forms, like chunks, powders, or chips. Say, for example, you can take aluminum powder, you can take aluminum wire, you can take aluminum chip, you can take aluminum chunk, whatever it may be. You can keep it in a porcelain crucible or in a board, and you can vaporize it. You can take the source material in many forms. And the vaporization technique is relatively inexpensive. That means the first one, this one is relatively, this one, the evaporative deposition is relatively inexpensive. You will get a good quality, not a very good quality, but a good quality of thin film with a less expense. But these are the you see, the electron beam deposition or pulsed laser deposition. It is very expensive, but you will get a very good quality of thin film from this pulse laser deposition or electron beam deposition, and you can get a complex film also. You can get some complex films also from this pulse laser deposition. There are some disadvantages also. The line of sight deposition gives a poor surface coverage and poor deposit uniformity. Somewhere you will find somewhere it is some thick, and you'll find somewhere it is very thin. So this you'll have uniformity. There will be some poor uniformity. But if you place some tool, or if you attach some instrument with this chamber, then it will give you more. It will give you more better quality thin film, but the cost will be higher. Poor ability to deposit many alloys and compounds. If you want to deposit some compounds, as because there is a large amount of heat is there, the compound will break down, the bond will break down. So you cannot deposit some alloys or compounds by this way. Poor utilization of vaporized material. The vaporized material can go in different places. Not you see the vaporized material here. The vaporized material here, you see I have shown you just this, just it is going from here to here, but it can go here, it can go here, it can go here. So there are some loss of your target material when it goes to the other places other than substrate. And high temperature required during processing. A high temperature, you have to deal with high temperature when this type of thin film you want to make. Now, this last one, high temperature required during processing. To avoid this temperature, what we do, we use another process that is called sputtering. We use another process that is called sputtering. What is sputtering? Sputtering is a term used to describe the mechanism in which atoms are ejected from the surface of the material when that surface is struck by sufficiently energetic particles. Now, say for example, this is a particle that stuck, that bombarded on that surface. So if it bombards this substance, some of the atoms of this substance will displaced from its position and it will go out. And these atoms will be deposited on the substrate. If you place a substrate here, this atom will be deposited on the substance. That is called sputtering. So you don't require the heat here. To avoid the heat, this sputtering method is used. So what are the reasons of sputtering? Use large area target which gives uniform thickness of the wafer. Wafer means that substrate. And control of the thickness by deposition time and other parameter. You can control the thickness by deposition time. That means you have a sputter for 15 minutes. Then you will know that the thickness will be, say for example, 5 nanometers. If you sputter it for 30 minutes, you will get 10 nanometer thickness thin film. So by knowing the time, you can control the thickness of the deposition time. You do not want any your instrument to see or to measure the thickness of your thin film. So by knowing the time of a sputtering, what do you mean by sputtering? Sputtering means bombarding of a material or ion or something to a target material, so that from that target material the atom will come out and it will go to the substrate. This come out of is known as sputtering. Even materials with very high melting point are easily sputtered. We don't require a heat. Say, for example, a material requires 1500 degrees centigrade to evaporate. we don't require 1500 degrees centigrade temperature. We just will sputter a beam of ion or beam of material to the surface of that material, and it will lose the material to form a thin film. Sputtered films typically have a better adhesion on the substance. These films, the atoms will have a better adhesion if you sputter a substance. A sputter can be formed from top-down by top-down method. So what is the basic model of that sputtering? This is the target, and if you hit the target, the material will come out and it will condense to the substrate. Now here also evaporation occurs. How evaporation occurs? You see here, these are the target molecules. So for example, these are the aluminum molecules. These are not attached. These are free. So it evaporated by not giving the heat, by giving energy by sputtering, and it is again condensed here. So the basic model is same. The source, and you evaporate that to the gas phase, then the gas will condense here. The basic model is same. I have a video for it. Just a minute. I see. Let's see if I can show you this video.
The use of thin layers of materials
শোনা যাচ্ছে?
made in many industries.
Yes, sir.
Glass, displays, and touch panels or solar cells all contain thin films. The most important coating process to produce these layers is called sputter deposition. How does it work?
শোনা যাচ্ছে কি?
Yes, sir.
Sputtering deposition is done in a vacuum chamber. The most common substrate for the thin layers is glass. The sputter system can have different sizes depending on the application. The source of the thin film material is a planar or rotary sputtering target of metal, ceramic, or even plastic. Molybdenum targets, for example, are used to produce conductive thin films in displays or thin film solar cells. At this point, the process starts. Air is continuously removed by vacuum pumps. The base pressure in the vacuum is around 10 to the -6 millibar, which equals about a billionth of the atmospheric pressure. Argon gas is introduced continuously to achieve a low-pressure argon atmosphere. A magnet array inside the cylindrical target generates a magnetic field. The target is filled with cooling water, which will dissipate the heat generated during the sputtering process. The targets are rotating so that the material will be utilized uniformly. A high voltage is applied to the molybdenum target. It creates a plasma, which is concentrated along the magnetic field. The plasma consists of argon atoms, positively charged argon ions, and free electrons. The positively charged argon ions are continuously generated by electrons hitting the argon atoms. The sputtering target is negatively charged. Therefore, the argon ions are attracted towards its surface. Let's see what happens.
This is
The argon
sputtering.
ions collide with the target and eject molybdenum atoms from its surface. This is what the sputtering process is all about. In a way, it resembles a game of billiards, don't you think? Layer by layer, the ejected molybdenum atoms are deposited onto the glass substrate opposite the sputtering target. But let's go back to the target material. No metal can be made 100% pure. Iron or chromium impurities in molybdenum targets are critical. Why is that? Argon ions don't distinguish between molybdenum and impurities. Impurities will also be sputtered and incorporated into the thin film. Nobody wants that. Impurities can negatively influence the thin film properties, the electrical conductivity, for example. Only highly pure sputtering targets can ensure high-quality thin films. And that's what Planze stands for. We are the only manufacturer to supply molybdenum at a guaranteed purity of 99.97%. Typically, the material is even purer. It is this purity that our customers rely on to create the best products in the market.
বুঝতে পেরেছ স্পাটারিংটা কি জিনিস?